Okay, so these are the notes for section 5.2. There are 3 pages. I'll probably do a different video, a separate video for each page, just to kind of break it up a little nicely. All right, we're talking about trigonometric functions. Now, the trigonometric functions, or trig functions, that you are familiar with are sine, cosine, and tangent. There are 3 more that we use quite a bit, and they are called cotangent, secant, and cosecant. These 3 new ones are directly related to the 3 originals that you know from geometry class last year. Okay, we abbreviate them. So, I mean, some of them are not that short. I mean, sine is just abbreviated S-I-N. So we don't say that as sin, even though it looks like sin. We still pronounce it as sine. And cos, we don't say cos, we say cosine. I mean, sometimes we're lazy and we say cos, but it stands for the cosine. T-A-N stands for the tangent. C-O-T stands for the cotangent. S-E-C, secant. And then C-S-C, that stands for the cosecant. Okay. Now, you in the past have, when you learned your sine, cosine, tangent, you used a little acronym called SOHCAHTOA. Now, SOHCAHTOA we will use later on, but that refers to just a general right triangle in any orientation at all, right? And so, if you remember, like, so stands for the sine is the opposite over the hypotenuse, right? So, you remember cosine is the opposite over the hypotenuse. And then the last one, SOHCAHTOA, is opposite over adjacent. Now, those terms work well when we have just a right triangle, sort of in any orientation, and the sine of an angle is the opposite side divided by the hypotenuse. But that acronym does not work that well sometimes when we are dealing with angles in standard position. And that's what we're going to start with here. So when we first start talking about sine, cosine, and tangents, like we are in this section, we are going to talk about the sine, the cosine, tangent, and cotangent, secant, and cosecant of an angle in standard position. So theta being the angle in standard position. We learned last unit, that the initial side is always on the x-axis, and then the terminal side of the angle is somewhere else in the two-dimensional plane. All right, and then the terminal side goes through some point x, y, x being the x-coordinate, so we can think about going over x and up y. So we can create a right triangle like you did with SOHCAHTOA, but this one is not, it sometimes is going to fail if we try to use SOHCAHTOA. So we have to get away from SOHCAHTOA while we're dealing with these. When we get back into some more word problems with later sections, we'll go back and we'll use SOHCAHTOA. But for now, forget about SOHCAHTOA, and you've got to memorize this stuff here. Okay, so let some point, x comma y, be a point on the terminal side of some angle theta. All right, and it's in standard position, of course. The distance from the point to the origin, so from that point over to the origin, we will think of as r. So we call it r because sometimes we're going to think of this as being a point on a circle that goes around the origin. So the origin will be the center of that circle. P will be a point on the circle. So think about a circle going around there. So now you can see why we're calling it r. In the past, we would have called it the hypotenuse of this right triangle, but here we want to refer to it as r. Okay, and that r, of course, is just the square root of x squared plus y squared, right? If we wanted to use the Pythagorean theorem for that. All right, so the 6 trigonometric ratios that we introduced a second ago, sine of that angle theta is going to be equal to the y coordinate of that point divided by the r. Okay. Let's move across. The cosine, that's going to be the x-coordinate of that point. So this side of the right triangle divided by r. The tangent is going to be y divided by x, assuming, of course, that x is not 0, because then it would be undefined. And sometimes the tangent of an angle will be undefined. Notice sine and cosine are never undefined, but all the other ones are sometimes undefined, depending on certain values of x, y, and r. Okay. All right, cosecant. Notice that cosecant is simply the reciprocal of sine. Right? Sine is y over r. Cosecant is r over y. Secant is the reciprocal of cosine. Instead of x over r, it's r over x. And cotangent is the reciprocal of tangent. So instead of y over x, it's x over y. Okay. So those relationships are more obvious here when we talk about the reciprocal trigonometric identities. All right, so you could flip them, or you can say sine is 1 over cosecant. Cosecant is 1 over sine theta. All right, so you have to sort of memorize these, and you have to remember which one's related. And so the one way that I help remind myself of which one is the reciprocal of which is when we look at the pair of reciprocals that are related to each other, there's only one co. So sine and cosecant. Cosine is the reciprocal of secant. There's only one co in the pair. Tangent and cotangent. One co prefix in the pair of two things. So I would never put cosecant with cosine. That would be two cos. I would never put sine with the reciprocal of secant, because then there's no co in that pair. So there's always one prefix of co in each of those pairs. Okay, so you really just have to memorize what these things are in terms of x, y, and r, and then also these identities. The reciprocals. You got to know which one is the reciprocal of which one. You just have to commit that to memory. Okay, so let's look at example 1. The terminal side of an angle in standard position passes through the point 5, 12. Find the exact value of all 6 trigonometric functions. Let's draw a picture. So 5, 12. Doesn't have to be exactly to scale, but if I go over 5 and go up 12, maybe something like that. Okay, so that's point P, 5, 12. All right, so what we want to do is, in every time we have a situation like this with an angle in standard position, we want to draw that angle in. Okay, and so we can think of it, we almost never draw the initial side in, but we draw the terminal side in. And then what we want to do is we want to draw a right triangle. And we never draw the right triangle over to the y-axis. It'll become more clear why that is. We always want to draw from that point down to the x-axis. Notice we did it up here. We drew this point down to the x-axis. We did not draw it over to the y. Even though this point is closer to the y-axis than it is the x-axis, we still want to draw it down, right? And so this is 5, and this is 12. And so we need to find r. So, we can use the Pythagorean theorem, or if you happen to know that there is a Pythagorean triple, 5, 12, 13. But if you didn't know that, then you would just use what? This, find r. R is equal to the square root of 25 plus 144. Okay, and that's, of course, 169. Square root of 169 is 13. So 5, 12, 13 is what we call a Pythagorean triple. Okay, so now what we want to do is, again, here's the angle, theta, right, in standard position, starting at the x-axis, going over to our hypotenuse, if you will. Okay, so what is the sine of theta? We don't know what theta is. We don't know what the angle is, but what is the sine of the angle? So sine of theta, and again, sine of theta is y over r, and so that would be 12 over 13. Let's go across. Cosine of theta. Cosine of theta is x over r, so that's 5 over 13. Tangent of theta, that is y over r. Y over x, so that is 12 over 5. And then now simply the reciprocals. So we want to do cosecant theta, and that's 13 over 12. It's r over y, so 13 over 12. Or we could just do the reciprocals, either way, but you got to sort of memorize all those. Secant of theta is 13 over 5. Remember, it's r over x. And then the cotangent of theta, and that's x over y. Okay. When you go to do homework in the textbook, the answer keys, if you look at the in the back of the book, they tend not to write. They just tend to list all 6 of these. So if this problem was something in the textbook, it would just list all 6. So you have to be, I don't remember what order they put them in, but they don't say sine of theta equals this. They just give us the 6 angles. So you have to be kind of careful of how they do it so that you can check your answers. All right, next one. Terminal side of an angle in standard position passes through the point -8, -6. So -8, -6, something like that. We can think about it going through that point. But again, we want to draw a right triangle. Always draw it from that point to the x-axis. And I draw in my right angle just to help me visualize where that is. Okay. And there's our point. So that means that x is -8. Yeah, if this was just a triangle in geometry class, we would just call that 8, and we would call this 6. But really, those aren't necessarily the sides of a right triangle, but the coordinates for this point. So we really still want to think of that as -8, -6. And then this is also a Pythagorean triple, 6, 8, and this will be 10. Now the r is positive. If you think about the radius of a circle, we never think of a radius of a circle as being negative. Now, I say that, but next year when you get to trig calc, there will be times when the radius is negative and it's something called polar coordinate. So just know for now, r is always positive. You can't have a negative r. So even though this is going down and it's going left, which is negative, the radius is always positive. Okay, so we've got our 3 sides. We've got x, we've got y, we've got r. We can write our 6 trig functions. So sine of theta, remember sine is y over r. So we have -6 over 10. Of course, we'll reduce that to -3/5. Okay. And then let's just work straight across. We have cosine of theta, and that's equal to x over r. So that's -8 over 10, but of course that reduces to -4/5. And then tangent of theta. Tangent is the y over the x, so that's -6 over -8, or 3/4. All right, and then the reciprocals, cosecant theta is -5/3. Secant theta is -5/4. Cotangent theta, 4/3. Okay. All right, so let's talk more sort of in depth of what these trig ratios are doing and how is it that we use them so much in mathematics. So the diagram at the left helps demonstrate that we can use the coordinates of any point on the terminal side of an angle in standard position to find the trigonometric values. All right, so a trig ratio is simply the ratio of any two particular sides. So for example, tangent of theta, that's the y over the x. So notice, even though we had 8, 6, and 10, -8, -6, and 10, we could have used this point right here, which was 5, and then we use -3 and -4, right? That's supposed to be a 4 in there, -4. So you could see that it doesn't matter what point we use on this terminal side, because the angle, like this angle here, is the same for both of those two triangles. So this angle here, theta, here we're in the first quadrant, this angle theta is the same for all triangles. So any point along this side, we drop down, we create a triangle, the ratio of the lengths is going to be the same. So the y over the x will be the same if we use this point or whether we use this point, right? 8 over 6 is the same as 4 over 3. So all those triangles, all the triangles that we would create if we drop them down to the x-axis would all be similar triangles. They would all have the same angle theta. So the trig ratio of tangent of that angle will be the same for all of those right triangles because the ratios of them will all be the same. And so that's how the trig functions work, and why the calculator can give us the tangent of any particular angle, so long as that angle's in any triangle, and it is the acute angle of a right triangle, then the ratio of the opposite and adjacent, or in this case, the y over the x, will be the same for any triangle, any right triangle that has that same angle theta in it. All right, this is true, again, the ratios are the same in both of those triangles because the two right triangles in the diagram are similar, right? And that's one way that we could create, how we can create similar triangles is if we had in a right triangle, if we have two sides and an included angle, right? So we had all kinds of ways of showing similarity. In this case, because they're right triangles, two sides and the included angle, right? The right angle and the two sides were enough to say that these are similar. So these are definitely similar triangles. And so we know that those proportion, that these ratios would be equal, they would make a proportion, okay? And that's the whole idea of why these trig ratios work, because regardless of the angle, if any triangle that has that acute angle of theta will have this same ratio, okay? If the angle is the same, the ratios will be the same, okay? All right, so now, last thing on this side of this page is talking about the quadrants. And we're concentrating here on the first three trig ratios, sine, cosines, tangents. The things that are true for those in this example are going to be true for the reciprocals as well. And so what we want to talk about here is notice that the trig ratios are going to be positive and or negative based on what quadrant they're in. So notice here we're in the first quadrant. This point was in the first quadrant. All of the ratios, let's concentrate on the first three, are all positive. And so that's what they're asking us to do here. This one's positive, and this one is positive. We're not really creating a ratio here. We're just saying the sine is positive, the cosine is positive, the tangent is positive. Okay, now let's work our way through the other quadrants. Notice here we were in the third quadrant. Some of them are negative and some of them are positive. Which one of the sine, cosines, tangents, which one was positive? And you can see it's the tangent. So in the third quadrant, the tangent's positive, but notice the sines and cosines are both negative. That's because the y is negative and the x is negative in the third quadrant, and those are both over r, right? So those would both be negative. Think about the second quadrant, right? Which one of those is positive? So sine is the y, and the y is positive in the second quadrant, the y coordinate. So that's going to be positive. The x is negative on the left of the y-axis, so the x coordinate will be negative. And then sine, that's the ratio of the y and the x. So the y is positive, the x is negative, that ratio will be negative. And then finally in the fourth quadrant, the sine will be negative. The y coordinate down here will have a y coordinate that's negative. And then x coordinate will be positive. And then the y over the x, which is the tangent, that ratio will be negative. All right, so this is kind of helping us remember in which quadrants which things are positive. So in the first quadrant, all three trig ratios are positive. In the second quadrant, the sine is positive. In the third quadrant, tangent is positive. And in the fourth quadrant, cosine. So we have a little acronym as we go across, we'll go around the quadrants. So we have all, we have sine, we have tangent, we have cosine. So we say all students take calculus as a little acronym to remind us. Now, this is less important, but you do need to know this, right? But this is less important if we, when we create our triangles, if we carry our negatives throughout. If I had just written this as 8 and this just as 6, then when I make my ratios, they're all going to be positive because 10 is positive, 6, and 8. So I would erroneously have put my sines and my cosines in as positive. So if I remember this, I'm in the third quadrant. Tangents, the only thing that's positive, the other sine and cosine have to be negative. So I would go back and put in my negative values. And then, of course, the reciprocal of a negative is a negative. The reciprocal of a positive is also a positive. So we only do the first 3 quadrants, knowing very well that the reciprocal of a negative is a negative. The reciprocal of a positive is a positive. All right, and so all students take calculus is just a little acronym to help us remind ourselves which of the 3 original trig ratios or trig functions are positive in which quadrants.